Hi students, today we are going to start lecture 30 in our aerospace engineering course, and today I'm going to discuss the aircraft equations of motion. I'm Dr. Ranjan Ganguly. Now essentially for this derivation, which is the beginning of what we can say flight mechanics part of this course, we will consider the aircraft to be a rigid body. And a rigid body is a solid body that does not go through deformation or change shape. So if you are somebody who has studied courses such as strength of materials, you know in such course the bodies are considered deformable. But in a rigid body, there is no deformation. So it's something you essentially study before you study strength of materials. For example, if you have studied courses such as dynamics, then the bodies are treated as rigid bodies there. Now there is a way to actually define rigid bodies more formally, which is good to keep in mind. For example, let us consider this particular body as a rigid body. Now, if we subject this body to several forces, for example, F1, F2, F3, what's going to happen is that there are forces and also moments which are going to act on this body. Now, if this body is a rigid body, then the distance between any 2 points on the rigid body will remain constant even though it is subjected to these external forces and moments. So for example, if I take 2 points A and B, which I have connected here by the red line, the distance between A and B is going to remain constant even if I apply these various forces to the body. So this is something which is very different from the deformable type of bodies which we consider in strength of materials, where you get change in the length and you get things such as strains and so on. So when we look at the aircraft equations of motion, we are going to consider the aircraft to be a rigid body, and we are going to consider four key forces which act on the aircraft, and these are lift, drag, propulsive thrust and weight. So these are the four forces which are going to act on the body. Of course, you know that lift and drag are produced from the aerodynamics, the fact that the body is moving through air. Propulsive thrust comes from the engine. So if you have chosen a jet or a propeller based propulsion system, this is going to be different. And of course, weight is something which acts downward because of the existence of gravity on Earth, and if you are on any different planet, the gravity on that planet. So let us now start looking at diagrams to get some idea about the nomenclature we need to create for deriving these equations of motion. So here I have drawn an aircraft which is essentially like a typical civilian jet. So let's look at it. Now the first thing we need to consider is the flight path. And the flight path is essentially the direction of motion of the airplane, and we assume this direction of motion is with some velocity v. So you can see here that there is the horizontal in red and the flight path in blue, the velocity v in the direction of the flight path, and this angle between the horizontal and the flight path is given by theta. So that essentially defines the flight path of the airplane. Now the next thing to look at is the thrust T, and this is at an angle alpha T to the flight path direction. So this I have shown in this green here. So this is the thrust T. This is essentially produced by the engine system which you have here. And as you can see, this thrust is at an angle alpha T with respect to the flight path. So this is something which acts at some angle to the flight path. Now the next thing to consider is the angle alpha between the chord line and the flight path, and this angle is given here. This is the angle alpha. So the chord line is actually the chord line of the airfoil section corresponding to the wing. So you see this chord line is going along the chord line of the wing or the airfoil section, and essentially the angle which this chord line makes is alpha with respect to this flight path velocity. So these are the typical nomenclatures in a general sense which we can consider to derive the equations of motion of the aircraft. So now let's start looking at the forces which act because of this motion. So as you know from our previous lectures, if we have the velocity v coming from the flight path direction, then the drag is going to be parallel to this flight path and the lift is going to be normal to this flight path. So the lift I have given here by L and the drag I have given here by D, and there is of course the weight which acts downwards towards the center of the earth. So it is essentially normal to this horizontal line here. So now with these angles, with these forces described here, we can start writing some of the equations of motion of the aircraft. So let's do it one by one along the different directions. So let's start by applying Newton's second law along the flight path direction. So this flight path direction is in blue and I'm going to apply Newton's law along this direction. So now since the velocity is in this direction, there is going to be a force in this direction, that is mass into acceleration. Acceleration is dv by dt, and if you see here it's in this direction. So now the force which creates this particular equation, this is going to be given by T cos alpha t, that's the component of thrust along the flight path, minus D. D is exactly along the flight path direction, and of course you are also going to subtract a component due to W, that is minus W sine of theta. So this angle between the vertical here in terms of lift and W is theta, so you clearly get this equation T cos alpha t minus D minus W sine theta. So that is essentially Newton's second law along the flight path. Now let's look at the Newton's second law normal to the flight path. So here again I have the flight path and normal to it is my lift vector, and also I have components of thrust and weight. So now this particular force is going to be balanced by the centrifugal force which is acting on this aircraft because of this movement here. So on the left hand side we have m v square by rc, which is the acceleration because of the centrifugal effects, and this is going to be balanced by the lift here plus t sine alpha t. So you see here t is like this in the green arrow. The component along the L direction is going to be t sine alpha t, and there is going to be a minus w cos theta component. So that's the component along this direction here. So this gives us the second equation, which is normal to the flight path. So again, let us take a good look at this equation here. Like I mentioned before, this term which you get here, v square by rc, this is the acceleration normal to the curved path with radius of curvature rc. And if you are somewhat rusty on these concepts, go back and refer to your books on basic dynamics and you will find these kind of equations there for bodies in rotation. Now you of course have m here, and when we multiply this by m we get the centrifugal force. So that's the centrifugal force term. So essentially the centrifugal force term is balanced by the components of thrust and weight and the lift. So now at the end of this derivation we have obtained these two equations which I have given here in two colors. The first equation is of course in the direction of thrust and the second equation is in the direction of lift. So these equations are general. They apply to bodies where acceleration is present, where all these angles are not necessarily small. So essentially alpha t and theta as defined here can be angles which are not small. Now even though this equation is very simple, it's actually something which we are going to simplify further for performance calculations. But do remember that this equation can be much more complex if we presume different and more complicated motion. For example, if we consider rotation about the axis, sideways motion of the aircraft, then these equations are going to become more complex and those are going to lead to what is known as the flight dynamics equation. So sometime very far out in this course, I am going to look at some of those particular equations there. So right now we are going to of course neglect all this rotation around the axis and sideways motion, and this is a reasonable model because we are going to use these equations for calculating some basic aircraft performance characteristics such as the maximum velocity of the airplane, the maximum rate of climb, and range and endurance. So these are some things which are very important for an airplane. These are the reasons for which an aircraft is typically designed. And so when you have an aircraft requirement coming from somewhere, they will often specify to you what should be the range of the aircraft, what should be the maximum velocity, maximum rate of climb, endurance, and so on, depending on why exactly they are trying to manufacture or design that aircraft. So now let's start to simplify this aircraft system or equations of motion for more specialized cases, such that the equations we obtain are amenable for our aircraft performance calculations. So let's start with this equation here, and I introduce two words here: level unaccelerated flight. So the fact that no acceleration is there means that the left hand side of these equations can be removed, so these become 0. And also level flight means that theta is 0, so essentially this angle theta between the flight path and the horizontal becomes 0. So if I substitute that in these two equations, I am going to get these equations here. So the first equation simply becomes t cos alpha t minus d equal to 0. So it becomes t cos alpha t equals d, and the second equation becomes t plus or L plus t sine alpha t equal to W. So again, do remember that when I substitute theta is 0, sine theta becomes 0 and cos theta becomes 1, which leads to these two simpler equations. Now there's one more fact I can use to simplify these equations. So the fact is that the angle alpha t, which is the angle between the thrust direction and the flight path, this is typically very small. So this may be a few degrees and so on. So I can assume the usual trigonometric simplifications that cos alpha t is approximately equal to 1, sin alpha t is approximately equal to 0, and then in these two equations I substitute this here. So once I substitute this, what I get is simply L equal W and T equals D. So for most conventional airplanes where this particular alpha T is small, and also I assume level flight in the previous slide, that is theta is 0, I can write these two simple nice looking equations: L equal W and T equals D. Now this picture here is very complex, so we have made several approximations here about alpha t being 0 and theta equal to 0. So I'm going to show you a simpler picture in the next slide. So this is the final picture we have got, and this is for the equation of motion for steady level unaccelerated flight. So here you will see the flight path angle is here. There is an alpha to the chord line. This alpha is typically very small, it's a few degrees. And so what happens is that there is the drag parallel to the flight path, there is the lift normal to the flight path, there is the thrust being generated by the engine here, and there is the weight acting here. And so I can now visualize these two simple equations, that thrust is equal to drag and lift is equal to weight. So when you are in level cruise flight, these things are going to be very important. Whatever drag is there, it's got to be balanced by the thrust, and whatever weight is there, it's got to be balanced by the lift, so the aircraft can essentially hang in the air and the aircraft can move forward. So let's summarize this lecture today. The summary is that flight mechanics will presume aircraft to be a rigid body to find equations of motion. Now this of course is a first level approximation which is pretty good for performance, but of course you can presume the aircraft to be a flexible body and derive the equations. You will get much more complex equations and you will get much more complex solution, but the basic physics can often be captured by this rigid body model. That's why it is pretty widely used. Now force balance and Newton laws are used to derive the equations of motion of an aircraft in flight, and we saw these equations, and we also saw that for steady unaccelerated flight the equations become very amenable. So you get T equal D and you get L equal W. Now, these amenable equations would appear to be extremely simple. So Can we use them in most situations? The thing is we can, because when we deal with aircraft performance, these equations are quite okay to use. So for example, I often need to calculate thrust, power, range, endurance, climb, glide, landing, takeoff, and these are for jet and propeller. So we will discuss these issues all in the next several lectures. These are essentially items which constitute the basic of aircraft performance. So essentially we will see that aircraft performance is very important because some of these things such as the range of the aircraft, the endurance of the aircraft, the fact about its climb, rate of climb, speed and so on, the fact that it should be able to glide, it should be able to land and take off obviously, and of course many of these things change depending on whether you are having a jet engine or a propeller engine. So this subject constitutes the basic thinking behind aircraft performance. So basically today's lecture we got introduced to the equation of motion of the aircraft, and we also saw that the equation of motion can be simplified very dramatically based on certain assumptions, and now we are going to use this equation of motion. Now where this helps you is that quantities such as the lift and the drag are of course difficult to calculate for a given airplane, but do remember that the corresponding quantities like the thrust and the weight are actually things which you may have. So for example, when an aircraft is designed, when it is flying, we do know the weight of this aircraft, and similarly when the aircraft is flying, it has a certain engine, it has a certain capacity, and so we know the thrust which is going to be available from this engine. So these things help us to actually figure out various performance parameters as far as the aircraft is concerned. So in the next lecture I'm going to start discussing about thrust required and available, which are very important for jet engines. So I'll end this video here and I will see you in a video sometime soon. See you then.